Okay, distinguished colleagues, welcome to the Coastal Zone Risk Mitigation and Management Working Group Online Seminar Series, number 12. I'm the host today. My name is Qinglan Li from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. It's a great honor to have with us today Dr. Kelvin Chen from the School of Atmospheric Science at Sun Yat-sen University. Dr. Chen is an associate professor of the School of Atmospheric Science of the Sun Yat-sen University. He is a PhD supervisor. He was awarded Talent of Sun Yat-sen University, the top 100 program. He got his PhD degree in energy and environment and bachelor degree in applied physics with the first class honor at the City University of Hong Kong. Dr. Chen has been dedicated to tropical cyclone dynamics and climatology, particularly on the size, intensity, movement, and precipitation. He has published more than 20 papers in SCI journals, such as Nature, NPJ Climate and Atmospheric Science, Environmental Research Letters, Geophysical Research Letters, Monthly Weather Review, etc. He led and participated in projects such as the National Key Research and Development Program, the General Program of the National Nature Science Foundation of China, and the General Program of Guangdong Basic and Applied Basic Research Foundation, the laboratory of tropical cyclone funded by Dr. Chen and his research team is gradually researching and developing tropical cyclone prediction products, providing meteorological service for the public. Today, Dr. Chen will share with us his study entitled Uncertainties in Tropical Cyclone Landfall Decay. I'd like to encourage all participants to actively engage in the discussion during the Q&A session followed the presentation. Your question and insight are highly valued. Okay, now please join me to welcome Dr. Chen to give his talk. Dr. Chen, please.
Thank you, Dr. Li. Can all of you hear me clearly?
Yeah, I can.
And I believe most of you can see my face, right?
Yes, I can.
Okay, great. All right. Before I start, let me share the screen with all of you first. All right. I think it's good now. All right. Hello, ladies and gentlemen. This is Kelvin Chen from the Shenzhen University, as what just Dr. Li introduced. Thank you for the AOGS invitation. And Dr. Li, Li Qinglan, I'm very happy to be here to share one of our recent work, that is the Uncertainties in Tropical Cyclone Landfall Decay. Hereafter, tropical cyclone is abbreviated as TC in short. And this work is done with Professor Johnny Chen from the Shanghai Typhoon Institutes and Asia Pacific Typhoon Collaborative Research Center. And two of my master students, they are Zhang Kaling and Wu Ye. They has been graduated. All right. Here is the motivation of my studies. In 2020, Li and Travolti published a paper on Nature they suggested that the decay of landfalling hurricanes is getting slower in a warming world, right? As shown here, the decay timescale tau. They study the landfall hurricanes over the North Atlantic in the past 5 decades. That is from 1967 to 2018. They found that the decay of the decay timescale tau here, tau, is getting longer significantly. We can see an increasing trend. That means the decay of the hurricane intensity after landfall is getting slower. And they attribute this slowdown trend to the contemporaneous rise of seasonal SST. Here, the SST we see an increasing trend, right? But please be noted that this SST is calculated by the 6-month average SST over this big box region. I suppose all of you can see my laser pointer. This box is very, very big. They found that the correlation between the decay timescale tau and the SST is very high. The correlation coefficient is about 0.72. As the SST is expected to increase under global warming, Lee and Roberty suggested a slower decay of landfalling hurricanes in a warming world. This is undoubtedly flattening to the coastal parties because the landfalling hurricanes could live longer over land and bring higher destructive potential to the public. So that's why this work is very alarming, and that's why they can publish this work to the famous journal. To support their findings, they did a series of model simulations by modifying the SST and moisture availability. Here is their model results. They spun up a vortex over the ocean with 4 different SSTs to about 60 meters per second, as shown here, right? 4 SST and spun up to 60 meters per second. After that, they set the lower boundary as land, such that they suppose the TC is now over land after the time 0 here. One set is for the moist simulations with moisture available. Another set is dry simulations without moisture. From the dry simulations here, they showed that the waters decay rapidly after landfall, right? Decrease very fast. And the decay of the water's intensity between the SST seems very similar, right? So they suggest that it is not sensitive to the SST. However, from the moist experiments, moist simulations here, results show that the decay is slower than those in the dry simulations, right? It decays much more slower than the dry one. This is actually reasonable because moisture is the energy source of the waters of the TC of the tropical cyclones. A key to note, they show that the decay of the water's intensity is sensitive to the SST, right? We can see a very distinct difference for the moist experiment. Results show that a warmer SST, a slower decay. This implies the role of the moisture. The role of the moisture is very important. Lee and Roberty thereby suggest that they validate that this higher SST would provide more moisture to the atmosphere, such that the hurricane would have more energy to maintain its structure, its intensity, and thus last longer and slower decay. So this is their model validation for the between the model and the observations. However, we questioned their work in the following 3 aspects. First is the sampling. second is the method, and the third one is the significance. I will go through them one by one. First of all, is the sampling. From the climatology, we know that the number of hurricane landfalls is very small. On average, 1 to 2 per year in the North Atlantic, right? As shown here, let's look at the top panels here. The bars on the plot are the number of landfall events. So we can see about 1 to 2 on average per year. And we can see that we have many gap years that are no landfalls, right? 0, that is 0 here. Thus, is the sample size large enough here, right? Just 1 to 2 per year only. So here is the questions. Besides, we found that the trend is sensitive to the determination of landfall events. For example, Lee and Traubopati determined that Hurricane Irene here, Hurricane Irene, is a landfall event. However, it could be not because it is over ocean at finer land sea mass resolution. As you can see here, this 0.2 is C and 0.5 degree resolution is also C. So therefore, this event is a marginal event. And again, let's look at this plot. The dots are the annual average decay timescale tau, the dots here. And the straight lines show the trend. Here, if the Hurricane Irene, as you can see the red box here outlined here, if this event is excluded, the trend becomes insignificant. All right, here, the trend decreased from 0. I suppose we can see that it's from 0.22 to 0.17 hour per year. And the p-values decreased from 0.05 to 0.12. So if the sample size here is small and the significance of the trend is sensitive to a single sample, can we conclude it is a robust trend? Here is another question. Once this sample is removed, the trend becomes insignificant. So here we think that we cannot conclude it is a robust trend. In our studies that are based on the raw data without smoothing that published in Nature 2022, we found that the trends are insignificant. Right here. As you can see here, if the land sea mass changed to 0.5 degree latitude and the land sea mass changed to 0.2 degree latitude, as you can see from the p-values here, the trend of the p-values is equal to 0.09 here. So which is larger than 0.05. So we think although the trend is increasing, but the trend is not significant enough. What's more, Lee and Traubopati applied a double 3-year smoothing from this small sample. That is, they applied the 3-year smoothing 2 times in a row. We think it is not reasonable because there are many consecutive years that have no landfall. As we just mentioned here, we see many gaps here. If you do double 3-year smoothing, of course, especially in here, the year between 2013 to 2015, there is a 3 years consecutive years gap here. Doing such double 3-year smoothing could create a lot of artificial data, which we think it is not feasible. Besides, as landfalling hurricanes are typically confined within a couple of days and small region, what Lee and Traubopati calculated is the 6-month SST, 6-month seasonal SST, I would say, from June to November and over such a large big area, so that we think this may not make sense. If we use the contemporaneous monthly SST, that is the SSTM here, and in this large box region, to calculate with the decay timescale tau, no correlation is found. The correlation coefficient is about 0.07, which is very weak. And now, if we use the daily SST, in short, the SSTD here, the daily SST in a 200 kilometer radius area from the TC center, we will see a negative correlation, but it's still weak. It's about negative 0.21. All right. Note that if this low outlier, this is the Hurricane Joanne, okay, is excluded, you will see that no correlation is found. The correlation coefficient is just about 0.03. So again, is the trend really significant, and can we attribute it to the warming SST? Right, very weak. And in our studies, again, based on the raw data and with dust smoothing here, we found that the decay timescale tau is increasing, right? We can see increasing trend from the figure, but we do not agree with what they suggest is significant. We think it is not significant and likely not primarily related to the warming SST, not related to warming SST. So instead, we find that the landfall decay is highly related to the effective area of moisture supply from the ocean. That is the AO in short here. The AO is the water area within 200 kilometer radius from the TC center. And from the analysis here, we find that the correlation coefficient between the tau and the AO is about 0.46. This is actually physical because larger the AO, the less the land surface friction and less energy dissipated, and thus the longer the tau. And a larger AO implies more sea surface entropy flux, so that more thermal energy is available for kinetic energy conversion, and the decay would slow down as a result. And now, when we take AO and SST into account together, the multilinear regression analysis show that the AO dominates significantly. Let's look at the regression coefficient here. We see that the regression coefficients of AO are much larger than those of the SSTs, right? The AO's ones are about 9 or 10 something, and those for the SST are 1 point something to 3 point something. So the one for the AOs is much larger than the SSTs. And if we look at the p-values here, the p-values for the AO are very small. That implies its significance, much significance than the SSTs, right? And this implies AO is the primary and significant factor that determines the landfall decay timescale tau. In addition, the results show that the contribution of SST are not significant. The p-value are all larger than 0.05. And if we look in the details, the results show that the contribution of seasonal SST, that is the SSTS here, is the least, right? It's just 1.68, and the p-value is very large. And reminder that the seasonal SST here is the 6-month average. Okay, it's the 6-month SST average in this big area. And now, if we take what I proposed in previous slides, that is the SSTM, the monthly SST, and the daily SST, we will see that the regression coefficient is higher. Okay, it's 3 point something. That means the SST, the monthly SST and the daily SST are more contributory than the seasonal SST. This shows evidence why we question the SST analysis conducted by Lee and Roberty. And given that the landfall decay is highly related to the effective area of moisture supply from the ocean, we think it could be mainly subjected to the landfalling track modes here, the landfalling track modes. Basically, we categorize the landfalling track modes into two modes. The first one is the hash rate mode and long hash rate mode. And in the long hash rate mode, we further categorize it into crossover, lingering, catwalk, and skirting modes. The hash rate thesis has the least ASC interaction after landfall. Therefore, the tau, that is the green plus sign here, is the smallest. All right. And whereas for the long hash rate thesis, we can see that they have the longer tau and larger AO. On the basis of the characteristics of landfalling tracks, the landfalling track modes are categorized by this decision tree. The hash rate mode categorizes hurricanes making direct landfall and experiencing partial ASC interaction after. Just like this. The crossover mode categorizes the hurricanes making landfall across the, some land masses. For example, the Florida, Caribbean Sea, Caribbean Island Sea, and the Yucatan Peninsula in particular. And for the lingering mode, categorize hurricanes making landfall by lingering along the coast. And the catwalk mode categorize hurricanes making landfall along the long and narrow landmass, just like walking over the catwalk bridge in the fashion show. Right, this is one of the example. And the skirting mode categorize hurricanes making landfall by skirting the coastline. And here is an example, is skirting to the US East Coast. All right. And this method categorizes over 98% of landfall events, while those uncategorized are all belongs to the long hash rate mode. And it requires empirical categorization owing to the mixture of the landfalling track modes and the complexity of the coastline and land masses. But anyway, no matter how this less than 2% events are further categorized into the crossover, lingering, catwalk, or skirting modes, the main conclusions of this study are not changed. If we divide the study period into two halves, that is, the first half is over 1967 to 1992, and the second half is 1993 to 2018. We can see that both the numbers of hash rate and non-hash rate modes thesis are found to be getting more. The number is getting more. And in particular, if we look at the proportion of the long hash rate thesis increased by 14%, from 30% in the first half to 44% in the second half. Besides, the decay timescale tau is comparable in the hash rate mode. while an insignificant increase in decay timescale tau is observed in the long half-track thesis. Therefore, we propose that the insignificant increasing trend of tau is mainly attributed to this insignificant increase in non-half-track thesis in recent decades. All right, and that's all about what we addressed in Nature 2022. Nevertheless, this is not the end of the story, of course, because Lee entrapolopathy and our nature studies are based on the samples over the North Atlantic, right? Bear in mind that. So it is therefore incomplete and not necessarily universal. Okay. To complete this, to be rigorous and comprehensive, we examine the global samples. We check the trend dependence on basin, data, study period, landfall intensity, land sea mass, and statistical technique. We find that the trend is basin dependent. For theses stronger than or equal to the hurricane force, that is the 64 knots here. Excuse me. Given the same study period, let's look at that. Some trends are increasing while some are decreasing. And some trends are statistically significant, whereas some are not. The figures here, x-axis is this time series in year, and the left y-axis is the decay timescale tau, and the right y-axis is the number of landfall events. The dots are the annual average tau, and the bars are the annual number of landfall events. And the straight line shows the trend at different study periods. So let's, for example, let's look at the red line, the red trend lines. That is the period of starting from 1967. The trends in the North Atlantic, the top one, and the Eastern North Pacific, and the South Indian Ocean here are increasing, right? The trend are increasing. And in particular, the one in the North Atlantic is significant. The p-value is less than 0.05 and is positive 42 hours per year. Whereas the trend in the Western North Pacific, in the North Indian Ocean, and South Pacific are decreasing and insignificant. So that's why the trend, we conclude that the trend is actually basin dependent. And second, we find that the trend is data dependent. Given the same study period, different sources of backtrack data exhibit different trends, even in the same basin, right? For example, here, let's examine the thesis over the Western North Pacific. The upper one here is manipulated from the CMA backtrack data. CMA means the China Meteorological Agency, while the lower one is from the CZWG, that is the Joint Typhoon Warning Center. And the trends, as we can see here, are obviously different. For instance, let's look at the red one starting from 1967 and the blue one starting from 1980s. The CMA red trend is negative 0.23 hour per year, while the JTWC red trend is negative 0.17 hour per year. And if we look at the blue trend, the CMA blue trend is significantly decreasing at negative 0.6 hour per year, while the JTWC blue trend is negative 0.35 hour per year. These inconsistencies are very likely due to the heterogeneities of operational procedures between the agencies, particularly the discrepancies in the estimation of TC intensity. And third, we found that the trend is study period dependent. That is, even within the same basin and from the same data source, the trends and their corresponding significance are not consistent with different study periods. As we can see here, most of the slopes are diverse and insignificant. For example, in the North Atlantic, the blue and the red trends are increasing, right? It's 0.42 and 0.38 hour per year, while the black trend here is decreasing. It's negative 0.11 hour per year. And note that the red trend is significant, while the black and the blue are insignificant. And in the Western North Pacific, the blue trend is deeper, right? It's deeper than the black and the red trends. And the black and blue are significant, but the red is insignificant, right? We can look at the p-value here. And in the South Pacific, the black, red, and blue trends are apparently different, right? So this is something about the study period dependent evidence. And fourth, here, we found that the trend is landfall intensity dependent, landfall intensity, right? Now the black cover I have removed here. The trends are sensitive to the landfall events conditioned by the thresholds of landfall intensity. The left column shows the landfall intensity larger than or equal to the gale force, that is the 34 knots, whereas the right column shows the landfall intensity larger than or equal to the hurricane force, that is the 64 knots. For example, in the North Atlantic, the black trend is significant for the TC larger than or equal to 34 knots. The p-value is less than 0.05. But it is insignificant for TC landfall intensity larger than 64 knots, right? It's not significant. P-value is much larger than the 0.05. And the red trend is insignificant for the TC larger than or equal to 34 knots, but significant for the TC larger than 64 knots. And in the Western North Pacific, the red and blue trends are increasing for the weak TCs, right? But it is decreasing for the stronger landfall, right? And the red trend is insignificant for the weak one and becomes significant for the strong one. All right, we can observe this from the p-values. And in the North Indian Ocean, all the trends are increasing for TCs larger than 34 knots, but decreasing for the TC greater than the 64 knots. So, and similar for the South Indian Ocean, all the trends are increasing. Decreasing for the 34 knots, but increasing for the strong landfall, right? Larger than 64 knots. So a great difference between the different landfall intensity threshold. And next, we found that the trend is land sea mass dependent. Song et al. Found that the decay timescale tau is significantly increasing for TC greater than 34 knots. So let's look at the left columns here. It ranged between 0.18 to 0.33 hour per year. However, we found that it is not significant. Our research did not find significant results. It's likely due to the resolution of the lengthy mass. The one in Song et al. Is 1.25 by 1.5 degree latitudes based on the JRA 55 VNS data. Ours is 0.1 by 0.1 degree latitude based on the ETAPOP1 data. This suggests that the trend is sensitive to the determination of landfall events, which is consistent with what we point out in Nature 2022. Lastly, we found that the trend is statistical technique dependent. The trends deduced from the season level tau and the event level tau are different. The white plot outlined in blue is the one we have discussed, which is at the season level. The left plot outlined in red is similar to the white plot, but at the event level. They are very similar, right? At the x-axis is the EU, the left y-axis is the decay time scale tau. The dot for the tau for all landfall events, and the straight lines shows the trends at different study periods. Therefore, 1 year could have more than one data in this case. That means the weighting or the loading of the trend is therefore not evenly distributed, which is different from the season levels. And now, for example, for TC greater than 34 knots in the North Atlantic, the red trend is negative at the event level, right? So minus 0.02, but positive for the season level, right? Positive 0.15. All right, and next, after we know all the trend dependence, let's revisit the landfalling track modes. In terms of the landfalling track modes, it consistent to what we propose from the North Atlantic samples, right? What I just shown in the first part. The global samples also show the decay time scale tau has the positive correlation with effective area of moisture supplies from the ocean, AO, right? Positive 0.3536, positive 0.44, positive 0.55 here. And we can see that the hard-strike TCs concentrate at the low end, while the long hard-strike TCs concentrate at the high end. The correlation is particularly high for TCs at landfall intensity greater than 64 knots. The correlation coefficients, which 0.55, if outliers, that is the tau greater than 200 hours, are excluded. It is noted that the correlation is weaker for TC greater than 34 knots because it also counts the TC between 34 knots and 64 knots. That is the TC between the tropical storm and typhoon intensity. This suggests that the inclusion of this relative weak TC would reduce correlation among this weak landfalling, would reduce the correlation, okay, from 5.5 to 0.36. And among these weak landfalling TCs, some decay slowly over the small AO, while some decay very fast over the large AO, right? The reason leading to such large variance could be a combination of the following. The first, less organized structure of a weak landfalling TCs introduce uncertainties. The associated eye wall, wind circulation, and even the lower tropospheric low pressure center are often difficult to be observed or identified. Second, the weak landform TCs proposes small inertial stability, such that they are readily influenced by environmental perturbations, for example, the vertical wind shear and moisture evacuation and underlying surface, for example, surface roughness and the moisture availability. And third, the advancement of science and technology. For example, the higher sensitivity and accuracy of measuring instruments. And the increase in the inland observations, for example, the broader network of weather stations and radars over the recent decades could prolong the best records. In particular, I'm sorry, because the figure is too large, it may be cause some delay. All right, in particular, the weak Haastrike Western Pacific TC that make landfall on China and Indo-China are found to last significantly longer over the past decades. Right, the tau is increasing. It is based on the CMA best data. While the strong one, that is the white column, while the strong Haastrike ones did not. The p-values are very small for the weak TCs, but very high for the strong TCs. Meanwhile, the results also show that the weak Haastrike records are getting more, and threaded further inland. But from the strong landfall TCs one, we do not see such results. And I believe most of you know that it's well known that the landfalling track modes are evidently subjected to the peripheral large-scale steering flow associated with the subtropical high. And this figure shows the change in the subtropical high in the past decades. The blue is over the first half period, and the magenta one is over the second half period. We see that the weakening, that is the eastward retreat of subtropical high, shown by the contour lines here. The contour lines is the subtropical high. And we see that over the Atlantic, the subtropical high shifts the TC activities eastward, such that more TCs make landfall on the Caribbean Sea, the Caribbean islands and the Yucatan Peninsula, Florida, and US East Coast in the long Haastrike mode, right? Because it shifts more eastward, more long Haastrike modes appears. This is consistent with the increase in tau of strong North Atlantic landfalling TCs that we shown before. And conversely, the strengthening, that is the westward extension of the subtropical high over the Western Pacific, shifts the TC activities westward, resulting in more Haastrike landfall events on China. And this agree very well with the decrease in tau of the strong Western Pacific landfalling TCs over the past decades. And the attribution to the change of North Atlantic subtropical high is not yet clear, whereas that over the Western Pacific is suggested to be partly due to the atmospheric response to the observed Indian Ocean Western Pacific warming. All right. And to conclude here, we question the Lee and Roberts study by providing additional views and evidence. We conduct a series of studies showing that the trends are uncertain, insignificant, and not universal. The trends are found to be based on data, study period, landfall intensity, land sea mass, and statistical technique dependent. The decay highly depends on the landfalling threat modes and likely result from the subtropical high variability rather than SST with the AO, that is the effective area of moisture supply from the ocean, playing a vital role. So here, please be noted that we should not take a part for the whole. There is no consensus about this matter yet. All right, so we should interpret the trend carefully before any broadcasting, including the citations, the social media broadcasting, or in the education, right? We have no consensus yet. And these are the reference I cited in this PPT. And that's all of my sharing today, and wish AOGS all the best. And thank you very much.
Okay, thank Dr. Chen. Understanding the uncertainty associated with tropical cyclone landfall decay is crucial for disaster risk management. Dr. Chen's research provides us a very valuable insight on this matter. Thanks for Dr. Chen's excellent report. So are there any questions from the audience? You can just ask question directly or type your question in the chat box.
Yeah, I have a question.
Okay, go ahead.
Okay, the question is in one of the equations where you have used decay time equation, which has a relationship with SST. The coefficient were, let's say, equal in magnitude. It was around 3. But if you see, the direction was kind of positive and negative. So does that mean the daily SST has a opposite effect compared to the monthly one?
All right, this is a very good question. Let me go to the slide and show you the relation, because the figure is a little bit large. Please wait a moment. I will go to that slide. Minimized windows. All right. I think Monhit, right? Dr. Monhit make a very good questions that we can see that in some SST, the regression coefficient shows the positive relationship, right? The positive 1.68, positive 3.86 for the seasonal SST and monthly SST. But it's very interesting that we see a negative regression coefficient for the daily SST. So here we guess, okay, we think it could be the negative relationship for the daily SST could be due to the upwelling, the undersurface, the underlying surface, the upwelling water from the subsurface, such that the TC would cool or slow down by the daily SST. It means the TC for this one could be related to the lingering mode, right? As what I mentioned, we have different track modes. One of the mode is the lingering mode. If the TC lingers around the coast, right, around the coast for a longer time, that means the upwelling effect would become very significant. So that's why it could contribute negatively, right? If the SST upwelling is strong, that means the negative times negative becomes positive and increase the decay timescale tau. So this is what I think. I don't know whether I can address your question, Mohit.
Yeah. Yes, sir.
Mm.
You have addressed my question. Thank you.
Good observations. Nice.
Okay, any other questions from the audience? Okay, I also ask one question. So Dr. Chen, the factor you considered, including SST, also like the method, also like the subtropical high, but have you considered the influence from the vertical wind shear? I mean, including the near the coast, also after the landfall, the vertical wind shear, the influence from this factor to impact the decay speed?
This is another good question. Right now, we still do not start this analysis yet. Maybe someone could follow up this and calculate the and see how the vertical wind shear affects the landfall decay, because it's somehow difficult because when the TC make landfall over land, and very significant vertical wind shear would be observed. So I suppose the vertical wind shear for the samples for the samples would be very similar. But I do not I'm not very sure about this. Perhaps Dr. Lee can test it, or all the audience all the audience here can make these examinations.
Yes, from our study, we found like in these 40 years, the vertical wind shear somehow is decreasing, have the trend, like the decreasing trend, it getting smaller. Probably this will also will influence the decay speed, the decay. We also found in some study, we also found that there's a trend. And also in your study, you remove some, like the sample, you remove some sample. Do you think that method is reasonable or not?
Actually, from our studies, because when we remove the samples from a small total of samples, this could be problematic. But what we did is remove the samples from the large number of samples, so the result we think should be significant.
But what you removed is the outlier. It's a very important point that will for sure will influence the result.
Yes.
Right.
For example,
for this slide, this Jan.
Yes.
19,
so we do not really neglect these results. So we shown and we discussed one is without removing, and one is all the raw data. I mean one is for the raw data, another one is by removing some outliers. We discuss both situations together, and we found that actually it's not very significant to the trend, to the decay timescale tau.
Oh, you mean remove is not the removed sample is not sensitive? Oh.
Yes, you're right.
Okay.
For example,
okay.
Not very sensitive.
Okay. Any other question from the audience? you can also type your question in the chat box. Okay, if there's nothing else from the audience we need to discuss today, so let's wrap up our meeting. And once again, I would like to thank Dr. Chen and thank all the audience to attend and to give our talk and to attend the seminar. Thank you. Thank you for your participant. Thank you. So see you next time.
Thank you, Dr. Lee, and all of the participants here. Thank you, and see you somewhere in the conference soon.
Yeah. Okay.
Yeah.
Also, see you next time at the online seminar. Okay. Bye-bye.
Okay, thank you. Bye-bye.
Good. Congratulations, Dr. Chen.
Not really. Thank you for your invitation and all the AOGS members organization coordinations. Thank you so much.
Okay. Bye-bye.
Bye-bye.